red and green lines. All right. We good? All right. Okay, so we're talking about perturbations now. So far, I think we covered J2, and we talked about atmospheric drag. I think we briefly mentioned the third body perturbations. Moon? That's fine. That's right. Okay. So I think the point is I think we all kind of know what the perturbations are and why we're interested in modeling them. One more that we can talk about is the solar radiation pressure. So at low altitudes, we're concerned with atmospheric drag. That's kind of an environmental perturbation that heavily influences satellite orbits. But at higher altitudes, like say geostationary altitudes, we're more concerned with the effects of sunlight on the satellite. There's not much going on in space, except, most of the satellite dynamics are modeled in the two-body problem, but with a lack of other factors, the sunlight becomes a serious player in the satellite's dynamics. So before we start talking about how the solar radiation pressure affects a satellite orbit, we'll talk about what solar radiation pressure even is. Does anyone know what solar radiation pressure is, besides from looking at the slide? What is it?
Oh, it's a photon that comes out of the sun that bombarding the surface area of your spacecraft, so it's like the bombardment is pushing your aircraft, such as that pressure.
Exactly. So what he's saying basically is the photons from the sun are bombarding your satellite and imparting a force on the satellite through the exchange of momentum. And that's exactly right. So what I have here is basically that solar radiation pressure, or SRP, I'm going to start calling it, is the force exerted upon a satellite due to exposure to solar radiation. It's really small. It is mostly dependent on the surface area of the exposed surface area, and also the satellite's mass. So if you can imagine a very lightweight satellite with a very large surface area and very reflective, you can start to see why maybe solar radiation pressure becomes a concern. So solar radiation pressure. Where it comes from basically is the solar flux. Basically the energy output from the photons coming from the sun. The solar radiation constant around Earth is about 1367 watts per meter squared. That's a variable number. It'll go up or down based on solar activity, but roughly speaking, this is a pretty good number. Most people use this number. It's a great number. Huge. Einstein, if you start looking at Einstein's mass-energy relation, famous E equals mc squared, you can kind of play with the numbers and kind of get an idea of the actual pressure exerted from this solar radiation flux. So you just do a quick manipulation here. We have E right up top. We know C is the speed of light. So pretty quickly we can get this number here, and that's the pressure that the satellites are exposed to here at Earth. That's 4.57 micronewtons per meter squared. So very, very small. So how we can back the force out from that? We know that pressure is force per unit area. So if we were to just multiply that last expression by area, that's pretty much where this force equation is coming from. And this CR is going to be it's similar to CD in the drag equation. It's kind of just a measure of how much your satellite's going to respond to the solar radiation pressure. So that CR coefficient will go from 0 to 2. 0 being completely translucent, so the sunlight goes right through it. No real effect from solar radiation pressure. 2 being completely reflective, so the satellite or the incident sunlight will bounce off of the surface and basically double its impact on the satellite. And of course, if we want to back out the acceleration from this, easily we just divide by the mass, And this is basically the equation that we're going to play with today. And this E hat vector here, it's a unit vector, basically says it's the direction from your satellite pointing to the sun. So you notice this negative sign in front of all these equations. Basically, if we define that unit vector pointing towards the sun, your experienced SRP will be pointing away from the sun. Does this make sense so far to everybody? Oh, because that's a typo. That should just say sun direction. We're not going to worry about sail orientation just yet. So this E hat vector is the direction to the sun. Okay, so now that we have a good understanding of what solar radiation pressure is, we'll talk about ways to utilize solar radiation pressure. You all maybe have heard of the term solar sails. And it's basically just a giant reflective surface attached to a satellite, which is used to basically get the largest exchange of momentum possible from the sunlight. So a big benefit to this is basically you have, now that we just finished talking about delta V, we talk about with sunlight, it's an infinite fuel source as far as we're concerned. So you have virtually infinite delta V. So that opens up the door for almost any satellite maneuver you want. It won't happen very quickly because, like we saw on the previous slide, we have a very small pressure which corresponds to a very tiny force. But over time, with infinite delta V, we can start playing with some non-Keplerian orbits. So maybe if you think about your standard orbit around a planet or even the sun, you can maybe stack orbits on top of your standard Keplerian orbits. So instead of having the sun in the center of your orbit, it'll be at the center plus or minus a couple thousand kilometers, which is pretty unique. Something you couldn't do with traditional fuel and propellants because you would just burn fuel trying to maintain that kind of orbit. So basically with solar sailing you can get reduced fuel costs, reduced propellant mass, frees up more space on your satellite for more payload, more sensors, and since we're talking about infinite delta V, as long as your satellite's still functional, you have a pretty long-lasting satellite as well. So here's our buddy Bill Nye. He's a strong supporter of solar sails. So I believe he took Astrodynamics under Carl Sagan, who was like Bill Nye 1.0 back in the day. And so basically, Carl Sagan was really into solar sails as well. He was actually designing a solar sailing mission to rendezvous with Halley's Comet back in the 80s. So Bill Nye has since developed his own interest in solar sails, and he's pitching this new solar sail called Light Sail 2. NASA made the first light sail. It didn't go very high. I wouldn't call it a success, but it deployed successfully. They're calling it a success, but it burned up in orbit pretty quickly. As you can imagine, if you're still at a low altitude and you have a surface area maybe this large, the atmospheric drag is going to tear this into pieces and really, really pull this thing back down to Earth. But here's a good idea of the size and scope of these solar sails that we're talking about here. So this is a 3U CubeSat he's holding in his hand. This is the actual satellite, I believe. It's the same satellite pictured here in the center. So this sail is 30. I don't quite remember. I want to say 32 meters square, but that might be that's another sail. This one's not quite that big. Do you think that's 32 meters? I don't think it's 32
square?
meters.
Yeah, square. Maybe 6 by 6 is 36, yeah. I think it makes sense.
Okay. Well, it's large. I mean, here's a cool dude sitting in a chair up here. I don't know if you can see him, but you can kind of see how large the sail is compared to him and even the bread loaf-sized satellite that he's holding in his hand. So
the yellow signs are probably a meter each or so. Maybe that's what they mean.
I think it's just tape.
Yeah, but I mean, I think that's.
Yeah.
Why would you have it so? I don't know.
I don't know. But, so there's a solar sail, guys. And here's more. So this is the solar sail we just saw. This right here is called Icarus. I think it's Greek mythology. It's basically, you heard the story about Icarus flying too close to the sun on wings of wax. The Japanese want to do it now with wings of mylar. So this is actually as far as I know, actually this is the case. This is the only successful solar sailing satellite that's propelled only by SRP. So this thing was launched up on some other satellite, ejected. It's spun to retract or to expand on this sail here, and I think it's on its way to Mercury right now. But what's cool about this guy is he actually gets attitude control based on these liquid crystals here, and they change their level of reflectivity, so you can get different torques applied on the satellite. And this guy right here is Sunjammer. This is the largest solar sail ever made. It's kind of hard to see, but there's people here. There's 4 people here. Very tiny, so it gives you a measure of how large the satellite is, or the sail is. And this one is the 32 by 32 meter squared, or 32 by 32 meter solar sail. This one likely will not go to space. I think the project ran out of funding, so now it's just a cool museum piece somewhere. But it was flight ready. So this thing was supposed to measure solar weather, they're calling it. It's basically just sun activity. Did you have a question back there?
You answered it simultaneously. I was going to ask about how to do maneuvers with the solar sail.
Yeah. So for those who are more interested in hardware and how this thing's actuating, perhaps. So again, this is you get torques from these liquid crystals here. This satellite, no liquid crystals, is as reflective as it is, but it's hard. I don't think you can see it in this picture, but at the tips of these vanes, there's actually smaller sails, you can call them, and those will actually change orientation. So you can get torques on each one of the ends of these booms here to get attitude control of this large guy. I'm not too sure how light sail does their attitude control. I think it's a series of like pulleys and tethers or something, but so I'm not quite sure.
Crystals polarize the light and adjust the reflective.
Yeah, so the liquid crystals, one way or another, will basically get really, really black or really, really reflective, and that's pretty much, aside from going translucent, which you don't necessarily want. Those are the 2 extremes you're going to get from the reflectivity. So you're either absorbing all the light or reflecting all the light, and yeah, I guess they just kind of modify their crystals' reflectivity based on their attitude needs. But yeah, right now this one's still on its way to Mercury. Okay, so when we talk about these solar sails and how do we maybe model this in our equations of motion? So before we saw basically the force and acceleration from solar radiation pressure, but if we start actually incorporating the sail's orientation here, this is kind of a more complete model of the solar radiation pressure. It looks pretty busy, but I'm going to demystify it here for you. This first constant here, nu, is what we're going to call the shadow coefficient. It's a constant from 0 to 1. If it's in 0, your satellite's in full shadow. If it's equal to 1, then you're in full sunlight. So that's pretty intuitive. So that basically turns on or off the SRP, whether or not it's the satellite is occulted by the sun or the moon or some other body. This P is the solar radiation pressure, which we talked about already. And this next term is going to be the astronomical unit squared over the position of the satellite squared, and position relative to the sun. So that term is basically how we determine the relative solar radiation strength, depending on where the satellite is. So this P naught, like I said, or this P sun, is 1367 or so, and that's measured around the Earth. So if our satellite leaves the Earth, we can't just keep using that same pressure. So that's why we have this term here. So it's another inverse square law. We have the area over mass, and then this next bit is kind of orientation dependent. So n hat is the orientation of your satellite, of your sail rather, and e hat's going to be the position of the sun with respect to your satellite. So you can kind of see that the orientation of your sail will determine the direction and magnitude of your SRP. And also the reflectivity we're calling epsilon here. If you'll notice this first term, if you have a fully reflective satellite, E will be 1. So this term goes away. So all your dynamics are going in the n hat direction, or rather opposed to the n hat direction. If you have a epsilon of 0, so completely absorptive sail, no n hat contributions, and all the experienced SRP is going to just go in line with the sun direction vector. So that's a pretty unique thing that the solar radiation pressure has on the satellite dynamics, and how it is dependent upon how reflective your surface area is. So we can sum that equation up into something smaller. If we collect all the constants that we talked about, make some assumptions, basically we have some characteristic acceleration which is going to be scaled relative to the orientation of the sail surface area. And what I'm trying to say basically is that if this is where the sun is, pointed in that direction, depending on your sail orientation, you'll experience any one of these accelerations. So you can see we can kind of point our sail any direction away from the sun at a cost of the experienced magnitude. So if we're completely perpendicular to the sun, then we'll get full magnitude. But if our sail is in line with the sun, we effectively turn off SRP.
Make a comment?
Sure.
I don't know if you said it. So n is the unit vector normal to your sail?
Yes.
Theta is the angle between n and the direction to the sun.
Exactly. So if I, this is our sun, right? That's what it looks like. So basically, if this is our sail, this is that E hat vector. And we're assuming, based on how I drew the picture, it's kind of skewed. So we'll say this is the sail surface normal. So this is perpendicular to the plane of the sail. So this will always be 90 degrees with the sail. Basically, this is n hat. And this right here is theta. Does everybody see this okay? Yeah, so that's all that's going on in these equations, basically. So what we're saying is the acceleration is dependent on this angle, and the strength will be dependent on the size and reflectivity of that sail. Yeah. Are there any other questions right now? Cool. All right, so now we're going to talk about how this perturbation affects the satellite's orbit. And what's cool about this is we can use this this perturbation to our advantage if we're smart. So say we have control over the orientation of our solar sail, and maybe want to raise the semi-major axis. We can orient the sail in a special way that will get that behavior. So I'm going to put up the vis vivo equation real quick. V squared over 2 mu over r. If you all recall, it's v squared mu over r, I think. Is that right? Okay. And we'll say that this is equal to 2. Is that right? Yeah. Okay. So we've seen this already. This is like the first month of class. So if we want to raise the sum major axis, for instance, and the Hohmann transfer will kind of help you understand what you should do too. What do you think we need to do to the velocity of this satellite? What's that? Increase it? Exactly. So if we were to increase the velocity here, we increase the satellite's orbital energy. A gets bigger. Don't forget about this negative sign. So basically, an increase in V makes an increase in energy, which corresponds to an increase in sum major axis. So from there, if we were to draw a line, this may be the sun direction line. So maybe the sun's down here. This is our planet. If we were to orient our sail so that our n hat vector creates a acceleration that's in line with the velocity, we would then increase the velocity of our satellite, resulting in an increase in the orbital energy and an increase in the sum major axis. So if we want to, say, raise the orbit of our satellite with a solar sail, just point it in line with the velocity vector on this half of the orbit, if our satellite's orbiting this way, that is. On the flip side, we want to lower the satellite's sum major axis, then we'll oppose the velocity with the solar radiation pressure, decreasing the sum major axis and orbital energy. So this is just an example of kind of a basic control strategy you could use using solar radiation pressure, and also a pretty good understanding of how we can use the perturbation in our benefit.
Another comment?
Sure.
Another way to see this, since this is continuous thrust,
Yes.
in a certain way, we can go to the Gauss variational equation and look at them and see what happens if you have a constant tangential acceleration. That should bring your signature axis up or down, depending on the sign.
Exactly.
So you don't have to write it now, but
No, that's fine. I'm gonna
look at that equation and see what happens.
pull it up anyway. All right. So, just for fun, we'll take a look at kind of what's happening here. Say we orient the satellite based on this first picture here on the left. So we're going to increase the energy of the satellite. Assuming I have a very large sail, very lightweight satellite, and I'm starting this satellite in the geostationary orbit, so about 42,000 kilometers from the center of the Earth. So in 1 year, it looks like theoretically I can raise the sum major axis by, this one says about 1,500 kilometers. That's pretty good. That's all for free. And that's just manipulating a force that's already there. And symmetrically, if we were to oppose the satellite's orbit, we can lower the sum major axis about 1,500 kilometers. But why do you all think, well, first of all, do we all remember what a geostationary orbit is? So it's a circular equatorial orbit. What do you think is happening here if we were to do these maneuvers? Why do you think this behavior, this is the eccentricity, why do you think it's increasing and then decreasing in a 1 year period?
That's for geostationary orbit.
This is geostationary, yep.
That's with J2.
So yeah, let's ignore J2, let's ignore every other perturbation. Right now we're assuming it's just the Earth and the sun, sunlight.
It's rotating with respect to the Earth and with respect to the sun.
Our sail, I mean, it would necessarily have to, yeah. But as we saw on that previous slide, our sail is oriented basically to assist velocity.
The sun is going to be changing as the Earth goes around the sun.
Exactly. So basically, you could think of it like the argument of perigee. Or, don't worry about the argument of perigee. Just the eccentricity vector is rotating around the orbit, basically, as the planet orbits the sun. So, say you start off at t equals 0 from a circular orbit. You start off with, you add this perturbation, and you're adding an eccentricity to the orbit. So you have an eccentricity that maybe points this way. By the time you get to the other side of the sun, your eccentricity is pointing that way relative to the sun. So that contribution to the satellite's orbit is now opposing or is acting towards apogee. Here, I'll draw it out. It's a lot easier to see. It's pretty cool. All right, so here's our sun. And here is our planet initially over here somewhere. And we're going to have a circular orbit. Our sunlight's going radially outward from the sun, right? So if remember like a Hohmann transfer, if we were to apply an impulse at perigee, what happens to apogee? Almost all of you got this question right on the exam. I see your finger doing something. Are you just pointing your chin? Yeah, increase, exactly. So yeah, if perigee's over here, it's a circular orbit, it's wherever we say it is at this point. You can basically see that if we're accelerating on this half of the plane, we're going to get some motion right here. So we're basically, I'm exaggerating big time, but apogee's going to be pushed out that way. So you can kind of translate this motion. Up here, maybe you have an orbit that now looks like this. So it's like an egg. So if we're speeding up this side of the orbit, we're going to blow it out this way. So now we have a very strange egg over here. And now we're going to blow out this end. Not quite circular yet. But I mean, if I drew my picture right, this last piece should be a little bit smaller. And by accelerating this, we now have a bigger orbit, also circular, by the time we get back to where we started. So that's something that's happening with SRP for free if we do nothing, but increase the sum-major axis continuously. And if we're very advanced, we can do other things like raise the sum-major axis, decrease the eccentricity a little bit quicker, and maybe dampen any kind of inclination that's starting to rise in the satellite's orbit. So with these other perturbations like J2, third body perturbations from the sun and the moon, you're going to get out-of-plane effects. So for instance, we simplified it here by just looking at the z position of your state vector. If you start off in equatorial orbit, you should have a 0 value for your z position. But if we just let our satellite drift, do nothing else to it, the sun and the moon will start to push this satellite out of plane. And using solar radiation pressure, we can return the satellite back down to its equatorial orbit, just basically by dampening those effects from the sun and the moon. And basically, yeah, do some cool stuff. Like maybe what's happening in this diagram is we're simulating a deorbit from the geostationary belt. We're using a solar sail to attach ourselves to a piece of unwanted space debris, raise it 300 kilometers into what's called a retirement threshold or a graveyard orbit. We release our debris to let it kind of float in space, and then we're bringing our satellite back down to the geostationary orbit to repeat the maneuver over and over again. Essentially doing this for free since we have infinite delta V and zero propellant. And that's basically what this graph is showing here, or these graphs. And now we're going to start to actually model this in MATLAB, so this will get pretty fun. Alright, so basically our model is just going to be the two-body equation plus SRP. And I'm going to start this at a pretty high altitude. I'm going to do the geostationary orbit. Okay. And it's going to be a 1-year orbit to raise the semi-major axis. So based on that diagram we saw in the PowerPoint, I'm orienting the sail to assist the satellite's velocity. And with that, you can kind of see here in this plot that I'm increasing the semi-major axis. Since we have no other perturbations going on, the inclination's not changing, and since we're in a circular orbit, we have pretty much an undefined RAN in argument of perigee here, but all the action here is in the eccentricity and the semi-major axis. And if you all look at those equations in the PDF that Dr. Bevilacqua handed you for the Gauss variation equations, you'll see kind of why there is no effect on the right ascension of the ascending node, the argument of perigee, or inclination. I think you'll find that the radial and tangential force components don't have any effect on those three orbital elements there at the bottom. So as we would expect, nothing happened. But for those of you who are more visual and like cool pictures, this is what we did. This is pretty cool. Whoa. No kidding. So this little circle here, I don't know if you all can see it very easily, but that circle there is where we started. And you can see we spiraled outward and increased the semi-major axis. And if we have a circular orbit, for the most part, you can kind of see why it's corresponding to such large circular orbits at the end of the simulation. If I do this just right, you'll see that there's no out-of-plane motion here. That's cool. But yeah, that's what we just did here with the SRP. But what if, for instance, you were to orient the sail facing the sun the entire time? So this is more realistic of what's happening to a satellite right now, because almost all satellites don't use solar sails at all. So if we were to exaggerate what's going on, have constant bombardment from the sun, this is essentially what's happening to our orbits, and you can start to see why SRP can be an issue if you're not using it as desired. So right off the bat, we see inclination problems, changes in the right ascension of the ascending node, changes everywhere really. And why do you think we're getting inclination changes now? And we weren't getting them before.
Is this with J2?
This is still without J2, but this time we're always facing the sun. The sail is always looking straight at the sun. Instead of orienting to assist the velocity, it's oriented to get the maximum SRP possible.
Earth's like an angle?
Sure, exactly. I think that's what you were just about to say. So the Earth is inclined. The orbit, I think it's it's tilted. Yeah, it's tilted like 23.4 degrees or something from the ecliptic plane. So essentially what you'll see is that the sun, if you're sitting on the equator, the sun is going to, in the summer, in the northern hemisphere, it'll be in line with the tropics, or the Tropic of Cancer, I believe it is. And in the southern hemisphere, their summer, the sun will be pointing at the Tropic of Capricorn. So basically, based on the equatorial plane, the sun kind of oscillates 23.5 degrees in a 1 year period. And that behavior is captured here.
These are radians, right?
These are radians. I didn't do a conversion. But if you want to see what's happening, if we have a large solar sail, and you want a circular orbit, and you don't model your perturbations properly, this is just J2, or this is just the SRP. This thing's trashing your orbit. It looks cool though, but far from a equatorial orbit. Granted, it won't be this exaggerated because most satellites don't weigh 50 kilograms and have thousands of meter squared solar sails attached to them. But if you're trying to get accurate models of your orbit, and you want to track your satellite, so you kind of send commands to your satellite or retrieve data, and you don't model these perturbations properly, you're going to think your satellite's here, when really, apparently it's over here. So these are big deals. And this is why we model perturbations. And this is why we start looking at the Gauss variation of equations and how to model those correctly, and we integrate them the right way. We can get a more accurate description of where a satellite is. And if we're clever enough, ways to manipulate perturbations to our benefit. So like Dr. Bablock was saying, some of the work he does in other research fields at lower altitudes, he plays with atmospheric drag to get benefits from that perturbation. So if you have multiple satellites flying near each other in low Earth orbit, and you want to catch up to one satellite or increase the distance, you can manipulate the sail surface area to capture more or less drag, and basically increase or decrease the spacing between those satellites. At higher altitudes, you see that we can maybe use solar radiation pressure as a propellant substitution and get some pretty fun orbits. So what I'll go ahead and do is upload these M files on Canvas for you all to play with, and there's an uncollected homework which is more for your benefit if you're interested in this type of thing. You can play with some of these parameters and kind of see how changing the surface area will manipulate your orbit, or if you're really inspired, you can start writing code to have new orientations for the sail and kind of see how that can influence your orbit. If you look at that PDF and look at the equations for the Gauss variation of equations, how they change the orbital elements, you can maybe design more intelligent controllers to orient your sail based on how their perturbations are changing in time. And that's basically what I got my master's thesis in. It's exactly that. Was basically the solar sailing with Gauss variation equations and getting desired behaviors from the satellite. So, are there any questions about any of this stuff?
This simulation, did you take into account when the Earth will eclipse the Sun, or the distance and difference, or the difference in distance between the satellite and the Sun?
So this particular one, I want to say no. I think this one's really simple, just to give you all an idea of kind of the strength of SRP and kind of its intuitive behavior. Yeah, this one's not doing any of that. But the simulations that pay my bills, yeah, those ones will include everything. It has that shadow coefficient for the sun and the moon. You know what? I'll pull one up if you want to take a look of kind of. There we go. So this right here is that same equation that was on the slide. It is this behemoth right here. So yeah, you can model this in MATLAB. Not necessarily easily. There's a lot of functions to give you. You need a function that tells you when the satellite's occulted by the moon or the Earth. You need a function for the position of the sun, so you know how to accurately model if it's beneath the ecliptic or above the ecliptic. And that's, yeah, I have that kind of captured in these functions here, basically. So this will give me the position of the sun, this will give me the position of the moon, so I can get third body effects from their gravitational potential. But yeah, at geostationary orbits, your model, all it really needs to consist of is a two-body equation, obviously, gravitation from J2, because that's still pretty powerful, and then the pull from the sun and the moon. And then you throw SRP on top of that and see if you can compete with those perturbations. And that's basically that was what I did my master's thesis on. But yeah, these models can get pretty complicated, and all this right here is just logic for my orientation. Here's your Gauss variation equations are captured in this line right here, basically, and this line down here. But yeah, this is just a fun example. If you can kind of decipher it on your own, this is a way you can use the Gauss variation equations to manipulate the satellite as you see fit. But yeah, that's pretty much it for SRP. If you guys don't have any other questions.
Are there any efforts to combine solar cells and solar panels?
So that gets tricky. The short answer is no, for the most part, because solar panels are pretty heavy, and solar panels you don't want them to be reflective. You want to absorb as much of that sunlight as possible.
But you get SRP from absorbing as well.
You do get SRP from absorbing as well. However, if I go back to this equation, your dynamics are different. So, assuming our sail is completely black, it's perfectly absorbing the sunlight so we can get maximum energy from it to power our subsystems. This whole term goes away. So instead of orienting your sail to get a desired perturbation effect, you're only getting this E hat contribution in your dynamics. So basically, the sun is only going to push your satellite away from the sun. It won't assist the velocity. It won't oppose the velocity. You can't orient it to increase or decrease inclination or anything. It's just going to move radially outward from the sun. And on top of that, it'll be 1/2 the magnitude of its maximum possible perturbation strength. So you see this 2 epsilon cosine theta term here on the right. That captures basically I guess we're talking about momentum, the elastic collision from the sunlight and the surface. So that's why you have that factor of 2, because you're getting that basically a double the impact from the sunlight on the surface. But if you have a completely absorptive surface, you're getting basically just the one-time effect from the sunlight, and you can't control its direction. So there's a number of reasons why you wouldn't want to couple solar sails with solar panels.
So is this something that's taken into account when you launch normal satellites or reflective surfaces? Do you actually design it to be as mapped or absorbed as possible in order to get rid of that?
Yeah, some satellites do. In fact, maybe they don't go so far as to design it to basically utilize the SRP. Maybe they do. But what they certainly do is they'll use what reflectivity the satellite does have to benefit the satellite's orbit. So maybe like slot maintenance, or basically just orbital maintenance if you want to make sure your satellite's not drifting too far out of plane. These perturbations don't happen or these large effects in the orbit don't happen overnight. So you can kind of, if you have a good model of how the SRP will affect your satellite, you can kind of anticipate when it'll push your satellite off course, and maybe if you want to change the orientation of your satellite in a different part of the orbit to make sure you minimize that effect or increase that effect if you desire. But yeah, there's been studies in the past where, I don't remember the application, but they were wondering why their satellite was going off course, and it was basically they didn't take into account the effect of sunlight. And once they did that, they were able to correct the orbit by using the SRP, but not with the solar sail, but just with its natural reflectivity. But yeah, in some way they do take it into account. Yeah. Yeah, I think that's it for today, guys. Thank you.